Good morning, everyone. It's a great pleasure to introduce David Conlon of the University of Oxford, who will speak on unavoidable patterns in words.
Okay, so to begin with, I'm going to talk about Ramsey theory very briefly, so that I can draw some analogies between what we're doing in this paper and what happens within Ramsey theory. So I should say to begin with that everything I'm going to talk about is joint work with Jacob Fox and Benny Sudakov. So let me just recall some basic facts from Ramsey theory. So if H is a K-uniform hypergraph, then R of H is the least integer n, such that every two coloring of the edges of K and K, so the complete K-uniform hypergraph on n vertices, contains a monochromatic copy of H. Okay, so for the most part, I'm just going to say things about what happens when H is itself a complete graph. So the standard case, the case that's sort of best known, is what happens when you're just looking at a normal graph and you're interested in KT. So in that case, it's known, so there's an upper bound of the form 4 to the t, and there's a lower bound of the form square root 2 of t. And this was proved in 1935. This was proved in 1946 or 7. So, and since that time, these have been improved by very small amounts. So the exact bound here is slightly larger, but basically it's been improved by a factor of 2. And this upper bound, I have a super polynomial improvement to it, but that's essentially all that's known. The exponents are still the same. So determining the constant here is a fairly difficult problem. Things actually get worse if you go up to higher uniformities. So if you go to KT3, then there's an upper bound proved by Erdős and Rado, and that upper bound is a double exponential. Whereas the lower bound in that case is actually just a single exponential that comes from taking a random hypergraph. So you can see here there's already a difference in terms of the tower height going on. And after this, when you start going higher, so there's something called the stepping up lemma, which I'll maybe lie very slightly, which basically says that once you know the value for this KT3, then you know what the value is for KT4. So it says that or KT in uniformity k plus 1 is between an exponential in the previous uniformity. You need to be a little bit careful, so you put maybe some constant here. But essentially you can think of this as being exponential in the previous thing. And the lower bound is 2 to the power of or k, let's make it t over 2, k. But again, essentially, you should just think of this as being kt. And this works for k greater than or equal to 3. And in particular, if you know what the value is for kt3, then you can just exponentiate on both sides to get the correct tower height going the whole way up. So technically speaking, this side is the part that's usually called the stepping up lemma. But basically, once you know this, you can determine what the tower height is. Okay. This is all I want to say about standard Ramsey numbers, but I've written it for comparison to what I'm going to talk about. So what I'm going to talk about principally is I'm going to talk about words, and I'm going to talk about patterns in words. And both of those I want to think of as being strings of characters. So these are strings of characters from distinct fixed alphabets. I mean, it's just what you think it is. A word is just a word. And we're going to need some notion of what it means to be a subword as well. So a subword of a word W is basically a contiguous string of characters. So contiguous string of characters. From W. Okay, so if you have 1, 2, 0, 2, 2, 1, 0, 1, then that's a subword. So you're just taking examples, just taking a string, an interval inside. And I'm going to say that a word, W, contains a pattern P if we can substitute a non-empty word for each letter in P to obtain a subword of W. Okay. And again, let me give an example of that. So an example is, so let's suppose we take 1, 1, 0, 1, 0, 1, 0, 0, 1. Then this actually contains the pattern X, X, X. Because I can find a non-empty word that I can give to X that's then a subword within the thing. Another example might be 1, 0, 1, which looks like it might contain XX because you've repeated 1 and 1, but it doesn't because they're not beside each other. So this contains X, X, X. This does not contain XX. So that separator is important. Okay. So what we're going to be interested in is a sort of notion, a Ramsey theoretic type notion for words. So we're going to be interested in, so we say that a pattern P is Q unavoidable if any sufficiently long word over a Q letter alphabet contains a copy of P, or just contains P, I guess. Okay, so the standard example of this goes sort of back to the foundations of combinatorics in words. So there's a paper by Axel Thu in about 1906 and 1907, where he studied basically finding squares inside of long words. So the first observation is that, so example, is that XX is 2 unavoidable. So this is very simple. So you're looking at a binary alphabet, and you want to show that XX is 2 unavoidable. Well, if the first letter is 0, then the second letter can't be 0 because then you're in bad shape. So the next letter has to be 1. And then again, the next letter can't be 1, so it has to be 0. And it has to alternate. But if it alternates twice, then you get an X and an X. So Very, very simple. On the other hand, x, x, x is 2 avoidable. So there's an infinite binary string that contains no copy of x, x, x. And the example here is what's usually known as the Thue-Morse sequence. So, and the idea is simple. So you start with a 0, then you take its complement, which is 1, and you append it afterwards. And then you just repeat that. So 0, 1, the complement of that is 1, 0, so you just append it. And then you keep going, etc. And actually, it's not easy to show, but you can show that this contains no x, x, x. And actually, there's an elaboration of this that you can map this string to a 3-letter sequence that contains no XX. So actually, so using this, you can show that XX is 3 avoidable. Okay, so these are, again, just some simple examples. So again, this is not quite what we're going to look at. What we're going to look at is those patterns which are Q avoidable for all Q. So it's a sort of stronger notion. So let's say that P is unavoidable if it is Q unavoidable for all Q. And the sort of fundamental theorem here is a result by Bean, Ehrenfeucht, and McNulty, and also proved independently by Zeeman. So I think this paper was published in 78 and this in 82, but I do think that they're independent. And basically they characterized the unavoidable words. Now the characterization is a sort of algorithmic characterization. It says that a word is unavoidable if through some reduction process it can be reduced to some trivial word. But Zeeman found an equivalent characterization which is much, much simpler. So the theorem due to Zeeman says that a word is unavoidable if and only if it is contained in a Zeeman word. Of course, I haven't defined what a Zeeman word is, but...
That's presumably not the term he used, right?
Probably not, no. Although sometimes people do use those kinds of terms. Okay, so a Zeeman word is a very simple construction. So you start with, so Z1 is just X. So obviously a single letter is unavoidable. That's pretty obvious. Z2 is X, YX. So you take 2 copies of X and you plant Y in the middle. And again, this is sort of obvious because you'll get, just the pigeonhole principle will tell you, you'll get the same letter repeated twice and then you'll find something in the middle, okay? And basically you keep going. You take 2 copies of the thing and then you plant another letter in between. So Z3 is X, Y, X, Z, X, Y, X. And if you keep going, Zn is Zn minus 1 with a new letter in the middle times Zn minus 1. So these are basically the canonical configurations for unavoidability. And anything that's unavoidable will be contained in the sense we defined earlier in one of these. It's not actually always obvious to see that something is contained within one of these. And then this reduction process, this algorithmic process, can actually help with that. But I won't describe this. It's actually surprisingly complicated. Okay, so having defined this, and having said that this is canonical, I now want to ask a Ramsey question. And the Ramsey question is, basically, how long does your word have to be to guarantee that you contain one of these things? So let's let fnq be the least integer such that every word of length fnq over a q-letter alphabet contains a copy of Zn. So it's kind of what you'd expect. Okay, so one thing I wanted to actually mention before moving on is that so these things come up in combinatorics of words quite often, not just here, and they also come up in group theory, funnily enough. So they come up quite repeatedly in reference to the Burnside problem. So the Burnside problem is if you have a group with m generators, all of which have exponent n, is the group actually finite? And it turns out that in analyzing that, these words come up. These words and slight variations of these words. Okay, so getting back to it, we're interested in this Ramsey function. So what can we say about this Ramsey function? So let's just think about, well, f1q. So all we want is a single letter. So f1q is sort of is trivial. Okay. F2q, we're interested in finding x, y, x. So basically, all we want to do is we want to find two repeated letters. So it sounds like q plus 1 should be enough because you'll get two repeated letters, but that's not quite the case because basically, because of examples like this, you could get 1, 2, 2, 3, 3, 4, 4. Actually, just I guess 1, 1, 1, QQ. This has length 2Q, but it doesn't actually contain this Z2 because all of the same letters are beside each other, which is kind of annoying. But if you go one longer, then you do actually get what you want. So this is 2Q plus 1. Okay, so what happens going higher? So let me prove. Well, let me first mention that. Zeeman showed that fnq is less than or equal to an Ackermann function. If you think about this for a little bit, it's actually hard to see how you could come up with a proof that gives an Ackermann function, but you'll see in a second that there's a fairly easy proof that gives a tower type bound. So what I'm going to prove is I'm going to prove a lemma, and the statement looks a little bit convoluted, but the proof is basically a picture. So I'm going to prove that fn plus 1 q, so if you're trying to get a copy of Zn plus 1 with q letters, is less than or equal to fnq plus 1 times q to the fnq plus 1. If I'm being pedantic, I could put another minus 1 here, but anyway. Essentially what's happening here is that it's saying that fn plus 1q is less than or equal to q to the fnq. Everything else is sort of smaller order. So the proof of this, as I said, is a picture. So let's take a string of length fnq. Let's put a separator variable, then put another string of length fnq. put another separator variable, and keep going. So, and then at the end we get yet another one. And we're going to take lots of these. So the number of these we're going to take is q to the power of fnq plus 1. So the length of this word is what I've set up there. This is a proof, and I'll now tell you why this is a proof. So, so the point is that each of these guys...
The plus
When you
one's
say
not in the
lots-
exponent.
Sorry?
The plus one's
Oh, the
not
plus,
in
oh,
the
yeah, sorry.
exponent.
That's also true, but... all right, so, so each one of these contains a copy of Zn. So this is a copy of Zn, this is a copy of Zn, this is a copy of Zn. All we need to do is find two copies of Zn that are the same. And then, because I put in these separator variables, we'll be in good shape. So, but I've chosen this number here so that the total number of ways, the total number of possible words of length fnq is q to the fnq. So two of these words are exactly the same. And if two of those words are exactly the same, then certainly the copy, the Zeeman word within them is also exactly the same. So then you're done. So that's it. And actually, if you do this carefully, so corollary is that, and I should say all of this observation is due to Cooper and Rorabo. So the corollary is that fnq is less than or equal to q to the q to the q, repeated n minus 1 times, where q is 2q plus 1. Okay. So you get this, this nice, fairly simple tower-type bound. You can improve this a little bit. So let's let TNQ be the collection, be the number of words which contain Zn, but any subword avoids Zn. Then basically the same argument goes through. So what you can do is you can take this argument here and you can sort of replace this with TNQ instead. And if you do that, then basically the same argument goes through, because the number of these minimal words is at most this. I should add one there as well. So each one of these contains a Zn, so it contains one of these minimal things, and then two of them have to be the same if we do this. Okay, so that actually tells you that you get an alternative lemma, which tells you that actually fn plus 1q is less than or equal to fnq plus 1 times tnq plus 1 minus 1. So I'm only going to apply this when n is 2. So for n is 2, how large is T2Q? So what are the words which contain a copy of Z2, so this XYX, but any subword doesn't contain them? So there are only a couple of different possibilities. So one possibility is you take A, repeated 3 times. So that contains a copy of Z2, but if you remove one of the words, it doesn't. And the other possibility is you take A, B1 to the J1, up to BR to the JR times A, where each of these JIs is either 1 or 2. Yes. Okay. So so then, if you count these number of words, so this is basically everything. These are the minimal words. If you try and count these words, then it tells you that that this T2Q is at most 2 to the Q times Q factorial. And then if you plug that back into this lemma, you get, let me go back over to the other one. You get so it implies that F3Q is less than or equal to 2 to the Q plus 1 times Q plus 1 factorial. Which, for now, let's think of as being roughly Q to the Q. If you then stick that back into this Cooper and Rorabaux iteration as the base case, this improves this. So, so using the iteration, we get FNQ is less than or equal to Q to the Q to the Q to the Q minus little oq at the top with n minus 1 Q's in the tower. Okay? So all I've really done through this extra argument is I've replaced 2Q here by Q. And in fact, the only one that really matters is the top one because the rest are irrelevant to this whole estimate. Okay, but I've gotten this, this thing. So why would I care about this? So why would I actually care about getting from 2Q back to Q? It seems kind of redundant. But half an hour into the talk, I still haven't stated any theorems. So let me actually state some results. So the first result is that this is tight. In fact, it's tight basically completely up to the constants. So theorem 1, again, this is myself, Jacob Fox, and Benny Sudakov, is that for n fixed, FNQ is greater than or equal to Q to the Q minus little oq of height n minus 1. So really, this is tight up to just this term at the very, very top. The second theorem, sorry, I should say, we actually have two different proofs of this. So we have two proofs. The first of which uses a variant of the local lemma. But I'll come back to that in a second. The important part here is that you can't just use this for uniform words. It's not enough to just look at a uniform random word and do that. You have to do something smarter than that. And the second thing is we use a variant of the stepping up lemma. So we find a sort of stepping up lemma for these Zeeman words. The second theorem is, okay, so there's something not quite satisfying about this, which is that we've fixed n. And if n is fixed, then you don't really know what happens when you fix q and you let n grow instead. So it could be the growth doesn't need to be tower type in that case. But the second theorem, so theorem 2, again myself, Jacob, and Benny Sudakov, says that actually, even for binary alphabets, sorry, I'm writing that the wrong way around. FN2 it should be. Even for binary alphabets, the growth is tower type. So Fn2 is greater than or equal to 2 to the 2 to the 2 to the 2. We don't quite get the correct tower height, but it's off by an additive constant. So we do know that this thing is actually tower type. And I should mention that just as we finished the paper, we learned that this was independently proved by Cariol and Goller. And the third theorem is we looked more closely at the n equals 3 case. So for n equals 3, so I've mentioned over here that we have this bound that says that f3q is at most 2 to the q times q plus 1 factorial. So we improved this very slightly to 2 to the q times q factorial. So we improve it by a factor of q, and we match that with a construction. So it's actually true up to a constant, that this is the exact bound in that case. Pinning down the exact constant we think might be difficult, but this is our third result. Okay. So I'm going to talk a little bit. I'm not going to talk much about theorem 2. If I have time, I'll talk a little bit about theorem 3. I wanted to talk mostly about these two different proofs of what happens here for theorem 1. And what the ideas are. So let's start with the local lemma idea. So, and I'm going to focus on Z3. On Z3, which, let's recall, is x, y, x, z, x, y, x. Okay, so let's forget about the local lemma for a minute and think about what we get if we tried a random word instead. Okay? So if you tried a random word, then and let's just look for Z2 within a random word. So you write out your random word, then you'll expect that you're going to get 2 copies of a letter within root q of each other, actually. So you'll find a copy of a letter x and a copy of another letter x, and they'll typically be within something like root q of each other. Which means that if you want to get one of these things, then all you have to do is find 2 repeated copies of this and this. So it looks like the total number of possibilities there is q to the power of root q. So that's not going to give you anything close to this q to the q bound. In fact, it's even worse, because all you really have to do is find 2 copies of a 3-letter word of the form xyx beside each other. So if you find 2 copies of a word xyx, well, the probability of getting this is like q to 1 over q cubed. The probability of getting this is 1 over q cubed. And then on average, you'll find a copy of those. Let's see, what's the answer? It's like q. Basically, you'll find a copy within q squared if you do it out carefully. So random words are really bad. The local lemma does a little bit better than that. Well, it actually does quite a lot better than that, because it's able to space things out better, but it's still not particularly good at it. But one of the main problems here is exactly this thing, that typically if you take a random word, even if you take the local lemma, these letters will tend to be close together. I think in the local lemma, if you do it carefully, they'll tend to be at distance q over 2 instead of q. But you want them really to be at distance q. So the model that we work with, instead of working with a random word, is let's split our alphabet. So split our alphabet into t equals log q pieces of size q over log q. Say L1 up to LT. Okay, so, and then what we're going to do, the way we manufacture a word is we're going to drop, so here we're going to drop a random permutation of the first word. So we take a random permutation of L1, and we just drop it there. Then we take a random permutation of the second word, put it there, and then we keep going. So random permutation of the third word, or the teeth word. Okay, so then we'd like to go again. We've run out of alphabets we can use, so we have to sort of recycle L1 here, but let's use a different permutation. So let's use sigma 1 of L1 here, sigma 2 of L2, up to sigma t of LT. And we keep going. We start again with L1 and we keep going along there. So this looks quite like a random word. It actually, within each thing, it's a random word. It just has the property that any two instances of the same letter are very well separated. So we get this nice randomness within pieces, but if I have a letter X, the closest they can be is at the very end of this and at the very start of this. And that distance there is Q minus Q over log Q. So the very closest they can be is that. Okay. Now, if you want to get a copy of this Z3, so if you remember, Z3 is XYX, Z, XYX. Then you're going to have to find, firstly, an XYX. And any XYX is going to have two letters X, which are a distance basically Q apart. So you want to find, and that means that to find this, you're going to have to find two copies of this entire word somewhere. So you have to find a word of length Q that's repeated. Now, the total number of words of length Q is Q to the power of Q. And basically, at this point, you can use the local lemma to guarantee that these things are very spread out and you don't get very many of them. So the whole point here is that there's roughly Q to the Q possible words of length minus little o q, of length Q minus little o q. Okay, so with some work, this idea can be made work. In fact, if you're careful and you use the sort of asymmetric local lemma in the right way, you can make it work to give this tower type bound when n is fixed. But as I said, we also have this stepping up argument. So the stepping up argument, I'll give some of the details. I won't give a complete proof, but I want to give at least the idea. So it will be useful to sort of strengthen the property of, so we're interested in words that don't contain a copy of Zn. All right? But I'm going to strengthen the property slightly and look at, let's let SNQ be the set of words of Q-letter words which don't contain Zn, and so it has this extra property that basically there's a single letter, so there is a distinguished letter is a distinguished letter C, such that any word that doesn't contain this letter C doesn't contain Zn minus 1. So any letter, any subword not containing C avoids Zn minus 1. So I guess you have this word, and then there are certain instances of this letter C along the way, and the whole thing is Zn free, and any of these intervals is also Zn minus 1 free. Okay. And let's let MNQ be the size of this set. So then our stepping up lemma basically says that mn plus 1, so obviously if you're one of these things, then you're also Zn free. So the collection of these things where you have q plus 2 colors instead of q, and you're looking for Zn plus 1, is at least as large as mnq factorial. Right, so, and basically, once you have this, you're done. So you can use this local lemma proof to show, so using the local lemma, you can show that this m3q is at least q to the q to the q minus little oq. And then if you stick that in here, that will give the right tower height. Now, there's one thing that's slightly off here, because this is counting the total number of words rather than the Zeeman function. But the Zeeman function is at least the log of this. So you can actually collapse that tower, or that one thing, and get back the bound for the Zeeman thing. So it's a sort of, so what do I want to say? mnq is less than or equal to 2 to the power of fnq. Sorry, q to the power of fnq. So once you have a lower bound for this, you also get a lower bound for that. Okay, so the idea here, the rough idea, is, so let's take all of the words in here that avoid Zn. So take all W1 up to Wm contained within this set Snq. Take a random permutation of them and then concatenate them. Okay. So basically, so for each pi goes from 1 up to m to 1 up to m. Consider the word W1, W2 up to Wm. Sorry, sig pi of 1. Pi of 1. Pi of 2 up to pi of m. So if you look at this, this has m factorial words, and it doesn't work. Okay, so this is something very, very close to something that does work. So you take all of the words at the previous level, you mix them around randomly, and you concatenate them. But it doesn't quite work. So what you have to do instead is you have to start putting a distinguishing letter between these guys. So you have to come back, and you have to say, all right, so let's do this, but now let's put a distinguishing letter between each of these. So this is sort of starting to look like it might be in good shape, because if you dig out this distinguishing letter and you just look at any word in between, then because that's from this mnq, it can't contain Zn. So now you just need to show that the whole thing doesn't contain Zn plus 1. Again, unfortunately, it still doesn't quite work. It's very close to working, but the extra twist that you have to do to make it work is you have to basically look at the distinguishing letter in here. So let's suppose the distinguishing letter in here is C. In fact, it will be C in all of them. Then what you have to do is you have to replace the distinguished letter in C with C1. Sorry, the first one with C1, and the second one with C2. In the third one, you can go C1 again, and you alternate. So you replace the distinguished letters in each of these by basically you alternate the distinguished letters as you go along. And it turns out the case analysis is a little bit awkward, but basically you can make this work at this point. But the basic idea of taking all the previous words from the previous step and concatenating them works, or comes close to working. So, all right. So that leaves us with the third theorem. So let me recall the third theorem. So this is that F3Q is theta of 2 to the q times q factorial. So I want to demonstrate the proof of this by doing a magic trick. So I'm not going to talk too much about how this goes, but actually a lot of the idea is already contained within this magic trick. So if the chair wouldn't mind helping me. All right, so cut that deck. So lift part over to one side and then put another part on top. Okay, so I'm going to take the 5 cards on top, lay them out like this. So I sometimes have done card tricks at schools, and then I sort of ask them lots of silly questions about whether anybody's been to India and which of them has a black card. So I'll line up 5 children. The important thing is which of these are black. So if you can have a look at them and just pull the ones that are black towards you, basically. So now I'm going to try and name. I should say that I learned this trick from the book by Ron Graham and Percy Diaconis. So it uses something called De Bruijn sequences, which is relevant to what I'm going to say here. So, all right, so the first card here should be, sorry, it'll help me. I can do this in my head, but it helps me if I write down some stuff. So the sequences of zeros and ones here are this. So the first one should be the 2 of clubs. Is that right? So the one on this side, yeah. Yay. Okay. So the next one should be the 5 of spades. Okay, so all right. So the next one will be the 2 of diamonds. 2 of hearts, was it? Or not 2? No, this one in the middle, right?
Oh, this one in the middle. Sorry.
Yeah. 2 of diamonds. Yeah. Then the 4 of spades, and finally I'm going to get them all right at this point. The 8 of diamonds. So, all right. So what I'm writing here is what's called a De Bruijn sequence. So if let me just keep going for a second and see how far I get. That's a little bit awkward. Okay, so so this thing has the property that if I underline any 5 letters in a row, that's unique. So you can write out a 32-letter binary sequence. So you have a 32-letter binary sequence where any 5 letters in a row are unique. So this is unique, this is unique, this is unique.
Cyclically?
Sorry? Cyclically, yeah, it's going around cyclically. I stopped here because the process I was using actually only produces a 31-letter sequence. And you have to add an extra 0. And the extra 0 either comes here or doesn't, I forget. I think I have to add an extra 0 at this point. But yeah, so there are 32 possible 5-letter sequences, and all of them occur, basically. And the thing that I'm using here to produce it uses irreducible polynomials over finite fields. But there's a very simple way to produce these things. So let me try and do the same. So firstly, I should. Yeah, exactly. Yeah. Well, it's an Eulerian cycle. Yeah. So the idea, and Natty sort of already said, so these are de Bruijn sequences. And I'm going to try and produce an 8-letter sequence where every subword of length 3 is unique. And the way one can do that is you can write out all of the different 2-letter sequences. So there are 4 2-letter sequences, 0, 0, 0, 1, 1, 1, and 1, 0. And then I'm going to put directed arrows, so 0 or 1 attached to them. So like going from here to here, I'm going to put a 1 because I can get from here to here by appending a 1 at the end of the sequence and then just taking the last 2. So this is 1. This is also 1. Let's see. This has a loop which is 0. This has a loop which is a 1. Let's see. Going from here, you get a 0. What am I doing there? So
Is a 0 from the bottom to the left? 1, 1 to 1, 0.
yes. Yes. Okay. And then going back and forth here, you get so you get a 0 going this way, and you get a 1 going this way. Okay, so this thing has so everything has in degree and out degree 2, and it's also strongly connected, so you can get from anything to anything else. So in particular, it has an Eulerian cycle. So if you follow this Eulerian cycle and actually just write down the sequence you get as you follow this Eulerian cycle, then you get a de Bruijn sequence. So let's just try and go. So let's do 0. Maybe I'll use a different color. So you get 0, then 1.
Are you missing?
I might be missing 1. I think I have everything, actually. So let's say 0, 1. Let's go back and forth here. So 0, 1 again. Then 1, 1. 1, 0, 0. Okay. So if I've done everything correctly here, then that should be a de Bruijn sequence. So everything of length 3 should actually be different, and it should give everything. And the same idea works in general. So it works to give you to give you a de Bruijn sequence of any given length, of any given parameters. The point I wanted to make is that the proof of this is a sort of elaboration of this particular idea. Now, it's quite a serious elaboration of this particular idea. It takes quite a lot of weight. So it's actually very close to this to get the q factorial. Okay, but to get this extra 2 to the power of q really takes quite a lot of work. But I like that it was related to this magic trick. So let me conclude by just stating one question that I think is interesting. I have no idea where to begin even doing it, but so if you recall, we defined Q unavoidability. So you're Q unavoidable if you're avoidable over a Q-letter alphabet. Sorry, unavoidable over Q-letter alphabet. So the property of being unavoidable is actually a very strong one. You're saying that you're unavoidable for 2-letter, 3-letter, 4-letter alphabets. But we really don't understand what happens when you're just Q avoidable. So what happens when you're finitely unavoidable? So there's some Q that you're unavoidable up to, and then after that you're avoidable. We really don't know. So the Thu, this result of Thu shows that XX is 2 unavoidable, but 3 avoidable. The best that's known here is there's a result of Clark showing that there's some pattern, which I won't try and write because it's like 15 letters long, none of which seems to make any sense. But he has a pattern which is 4 unavoidable, but 5 avoidable. And it's interesting to conjecture that maybe there's a pattern which is q unavoidable for every q, which is q unavoidable but q plus 1 avoidable. That seems horrendously difficult. I would actually just be interested to understand some collection or some new collection of things which are q unavoidable for some finite q, but not beyond that. So I think there is actually some interesting questions here just in the combinatorics of words and connected to Ramsey theory of just trying to figure out what configurations are q unavoidable. Okay, so I will stop there.
Are there any questions?
Is there anything that is really closer to the original Ramsey? So you do 2 words and you can show that either this one or that one must appear?
There may be something like that, so you can ask for unavoidability for patterns, for collections instead, yeah. It may be the case, actually. I'd need to look more closely at these original results, Bean, Ehrenfeucht, McNulty, and Zeeman. They may also classify collections of words as being unavoidable, but I'm not entirely sure. Yeah, I need to think about it. But it's a good question, though.
Is much known about like counting the number of like occurrences of Zn, for instance?
No, I don't think so. You'll get some bend. So always once you get a Ramsey function, you can always do some standard saturation argument. So you just take out subwords. You're not going to get very many from that, though, because you'll be taking subwords. There are sort of n starting points. So there will always be something like n divided by fnq of these things. But I actually don't know beyond that. So we haven't thought about that.
Great. If there are no more questions, let's thank David again.